Hello and welcome everyone to today's seminar. Today I'm happy to have Zhao and Ben Hogan to discuss some new insights into radiation belts and the GEM radiation belt focus group today. So our first speaker today will be Hong. She is an assistant professor in the Department of Physics at Auburn University. She got her bachelor's degree in space physics from Peking University in 2011 and a PhD in aerospace engineering sciences from the University of Colorado in December 2015. After graduation, she started as a research associate at LASP, and in 2021, she became an assistant professor at the physics department at Auburn. Her research focuses mostly on understanding of the dynamics of energetic charged particles in Earth's magnetosphere using satellite observations, simulations, and through instrument and mission development. She is one of the chairs of the GEM focus group, System Understanding of Radiation Particle Dynamics through Multi-spacecraft and Ground-Based Observations and Modeling, which is what she will be discussing with us today. So Hong, if you would like to take it away.
All right, thank you so much. I'm going to share my slide. Okay, and I'll go to the presenting mode. Okay, I hope you are reading the correct slide.
Yeah, we're in presentation mode now.
Okay, great. Thank you. Thank you everyone very much for attending this seminar, and also thank you, Kyle, for your invitation to give this talk. So I will be on behalf of our focus group to talk about our GEM focus group. The title is exactly the title of our GEM focus group. It's called System Understanding of Radiation Belt Particle Dynamics through Multi-spacecraft and Ground-Based Observations and Modeling. And just a little bit side note and a little bit tip, if you want to propose a GEM focus group, better to go with a shorter name, because every time it kills me to just say the full name. And we don't have a good acronym of it. So far we just call it Radiation Belt Focus Group. But that's pretty much the side note. So today I'm going to briefly go over our focus group's goals, motivations, and talking about our past activities, and highlight a few things and talking about our current status and future plans. So the motivation of us to propose such kind of the focus group is certainly because we know that understanding the radiation belt particle dynamics is very important. It's of both scientific interest and practical need. However, traditionally, we had very limited observations, and often we only have single point measurements, which have limitations in spatial temporal coverage, and also this would have limitations in revealing the underlying physical mechanisms on the radiation belt particles. But luckily, now we have much more measurement capability, so we can really go investigate the radiation belt physics through the coordinated measurements from multiple spacecraft and ground-based observations, and further combining with theoretical and modeling efforts, we can further advance our understanding of radiation belt particles on both global and local scales. And also, GEM workshop style sessions are particularly beneficial to such kind of investigations, since we really need close collaborations between different mission teams and also observers and modelers. So the very broad goal of our focus group is to deepen understanding of radiation belt particle dynamics through coordinated multi-mission measurements combined with theoretical and modeling effort. So at the very beginning of our focus group, we identified a few specific topics. However, certainly those topics kind of like change over time, and we have our different focus topics for different sessions, which we'll talk about later on. But at least initially, we aim to focus on first, the improved understanding of radiation belt particle acceleration and loss on short time scales, because they often require a collaborative observation from different instruments, different satellites or missions. And we also aim to quantify the radiation belt electron precipitation into the atmosphere and understand the related physical mechanisms, which also because it often requires conjunctive observations. And then later on, after this talk, he will discuss a little bit more on his highlights on the electron precipitation. And we also aim to improve the understanding of the properties and spatial temporal distribution of radiation belt waves and their effects on particles. And finally, we want to advance our understanding of inner belt and slot region particle dynamics, since, well, they are often overlooked, but there are very many new things that have been discovered by the Van probes about them. So thanks to the GEM's very nice workshop style, we actually had quite some very interactive or engaged focus group activities in the past few years. So usually we have some sessions with overview talks and open discussions. We also have organized quite a few panel discussion sessions. And often we have general contribution sessions and joint sessions with other GEM focus groups to best utilize GEM's format. And we try to keep those sessions interactive as possible by dedicating time for open discussions and also encourage concise presentations to allow more time for question and answers. So more interactions, not just the presentations itself. And just a brief overview on the topics we have been focused so far. So there are quite a few overview sessions which we invite some scene-setting speakers to talk about outstanding questions in radiation belt studies and also future directions of radiation belt research and exploration. We have also organized quite a few different panel discussion sessions, including course wave generation, the radiation belt space mission status and results, the role of mesoscale processes in the radiation belt dynamics, radio transport versus local acceleration, the long-standing debate, and most recently, we have done a panel discussion on radiation belt loss, the great debate part 2. So apparently in this presentation, there's no way I can highlight all of them, which all of them show beautiful results, but I will be mainly focusing on one of them, the debate between the two acceleration mechanisms, radio transport and local acceleration for radiation belt electrons, to give you some highlight of our focus group activity. So this panel discussion was on a very long-standing question in radiation belt community: what actually energizes those particles to relativistic or even ultra-relativistic energies? And there's long-standing debate over whether it's radio transport or local acceleration of the two leading acceleration mechanisms. So for this panel, we invited 5 panelists, including Hailey Ellison, Mary Huston, Alison James, Solon Lechang, and Louis Ozicki. And moderators are our focus group chairs, and also special thanks to Sasha Jostov and Mike Hartinger. And we have very nice discussion, even though this was a virtual panel at that time, unfortunately because of pandemic, but we had quite some interactions with audience, and also we have beautiful outcomes, which resulted in 2 publications as I listed here. So the first one, led by Sasha, is almost like a summary of our panel discussion and also some specific results coming from that. It's published in Earth and Space Science in 2022. And the second one by Solon, which is more like an overview paper focusing on the results of the panel discussion as well, talking about differentiating between the leading processes for electron radiation belt acceleration, also published in 2022 in Frontier. So today, my presentation will be centered around this panel discussion results and getting some results from these 2 papers, but certainly I won't have time to discuss too details, so please feel free to check out these 2 papers if you want to learn more. The motivation behind this panel is, again, well, we have routinely seen the enhancement of relativistic and ultra-relativistic electron fluxes in Earth's outer radiation belt. Sometimes it can happen very rapidly within a couple of days or even less, a couple of hours. And they display clear energy-dependent behavior, just as this figure shows. Here, this figure is from Baker et al. 2019, showing the flux measurement by REP instruments on the Wellen probes for different energy particles. So the x-axis is a time for multiple years, and the y-axis is L shell. And we can see, even for these relativistic and ultra-relativistic electrons, their flux variations in the outer belt is still very dramatic. And also there's clear energy-dependent behavior across these different energies, even though their energy only differ by a factor of 2 or 3. So this suggests that the underlying mechanism of this acceleration are also energy dependent. That's what we want to really know about. And as I just mentioned, well, it's a quite good consensus among the radiation belt community that there are 2 leading acceleration processes. First one is so-called radio transport. This figure from Reeves et al. In 2013 show a very nice schematic about this. So essentially, radio transport is saying, well, we have to energize those less energetic electrons located at higher L shells by transporting them inward to the outer radiation belt region. During this process, the first adiabatic invariant is conserved. So since the particle is moving to a stronger magnetic field region, its energy would get higher. That's how it gets energized. And traditionally, radio transport is considered as an external mechanism since you are moving particles outside from the radiation belt to the radiation belt and energize them. And also, we would expect a positive radial gradient in the phase space density if that's the case. One of the competing acceleration processes is so-called local acceleration, which, as suggested by name, it's energizing less energetic electrons located at the same L shells by local heating of most likely coarse waves. And just as this schematic shows, we would expect a locally growing phase space density peak inside of the outer radiation belt by this wave-particle interaction, because this process essentially breaks the first adiabatic invariant and directly heat up those populations. And because of this, local acceleration is also traditionally considered as an internal mechanism. So we have identified these two leading acceleration processes for quite a long time. However, there are ongoing debate on which one is the actual mechanism, which one is more important for each population, and etc. And that's all behind our motivation to organize this panel to get a field consensus and to get our future steps. So coming out from the panel, what do we know so far? Well, we pretty much agree that, well, we know that based on the literature review, the energization of those relativistic and ultra-relativistic electrons can either be explained by one process or the other, or the combination of the two, which almost say we did not see anything. However, it is indeed the current consensus that the combination of the two leading acceleration mechanisms is the most likely explanation for energization of these very high energy electrons in the radiation belt. This schematic is from Lee and Hudson 2019 paper, shows this combination of the two mechanisms very nicely. So initially, we would want some radial transport of seed and source populations from outside of the radiation belt region to the radiation belt, create this positive radial gradient in phase space density. And then we would have those source populations generated coarse waves to locally heat up the seed populations, create this local peak in phase space density, which is often treated as a telltale signature in local acceleration. And after this peak is created by local acceleration, radial diffusion would work more efficiently to redistribute this peak, essentially to smooth out the radial gradient in phase space density and move particles inward and outward. For those particles be moving inward, they can further get energized to even higher energies. So it is our current consensus of the field that most likely both processes play important role in radiation belt electron acceleration. However, it is still undergo very significant debate on, well, how much quantitatively each mechanism contribute to the acceleration, especially to which specific population or energy of particles. And second, well, we do know that the Fock-Planck formalism works reasonably well on long time scales. Here, the long time scales refer to often days or sometimes even can be months or years. On that kind of long time scale, well, this Fock-Planck framework works pretty well. However, it remains limited in many ways, including, well, in shorter time scales, say if we want to do within a day or a couple of hours, it often meets very important variations on that time scale. So these are so far the things we think we do know of. And the panel also identified quite a range of limits and challenges in the things that we do not know. And apparently, I don't have time to go through each of them in detail. I will just provide some highlights. And if you feel interested, feel free to read the two references I put in the previous slide. So one of the limitations we have is the uncertainty in phase space density and phase space density radial gradients itself. Very unfortunately, well, phase space density is actually the physical quantity we want to study when it comes to the radiation belt particles. Since flux itself is not physical, it might correspond to different populations at different times, and the interpolation need to be very careful. However, the phase space density calculation would rely on too many things and itself may not be always accurate. For example, the limited spatial temporal resolution or coverage in observations would cause a little bit troublesome in phase-space density calculation, and especially in phase-space density gradient. For example, this figure from Oliver et al. In 2021 shows the phase-space density calculated by using the valence probes measurements. Here we can see two passes by the two valence probes. The yellow pass is from valence probe A, is going from a low L region all the way to high L region, is going through an outbound pass. While valence probe B at the same time is going through an inbound pass from high L region all the way go to low L region. And well, if we only look at the phase-space density radial gradient they measured, we can come to a conclusion saying, well, in this case, local acceleration happened since it creates a growing peak in phase-space density inside of the outer radiation belt, which is clearly a local acceleration signature. However, the authors really look into detail about conjunctive observations of the two probes. They found out this straight lines, which is connecting the instantaneous phase-space density profiles by the two valence probes. And all this instantaneous phase-space density radial profiles suggest that the radial gradient at this limited L shell range is always positive, which is actually considered a signature as radial diffusion. So this local peak we're observing in valence probes observations is very likely just because, well, when valence probes go through high L region, the enhancement has not happened yet. When it goes to lower L, suddenly the enhancement happened and it measures overall enhanced phase-space density, even though it does not mean there's necessarily a local peak in this case. So this is a very good example to show that with limited spatial temporal coverage, we really cannot tell too much about the underlying acceleration mechanism purely by inspecting the phase-space density radial gradient alone. And certainly, because phase-space density calculation need to use magnetic field models, intrinsic uncertainties in magnetic field models would cause uncertainties in phase-space density itself. And there are some papers demonstrated that, well, if you are using different magnetic field models, you would even get very different phase-space density, or even gradient in phase-space density would influence a lot of the interpretation of the results. One of the mitigation factor that Ozeki et al. 2019 talk about is to compare observation of magnetic field versus the measured magnetic field. If they are too different, you just do not use that time to do any phase-space density calculation. However, just keep in mind that the magnetic field model is global, so there's essentially no way we can get a direct comparison with a global magnetic field model. So that always into the uncertainty in phase-space density and phase-space density gradient calculation. And certainly, even though Fock-Planck framework works pretty well on long time scale, it itself comes with a set of limitations. Here are just a few examples. First, Fock-Planck framework is intrinsically diffusive. And unfortunately, we know there are non-diffusive processes in radiation belt studies, and it's not well quantified, and we don't know how much it contributes, even though there are some studies suggest that they do contribute quite a lot to radiation belt dynamics. However, Fock-Planck framework cannot well cooperate those non-diffusive processes. Maybe one way to compensate for that is to add unseparated source and loss terms. However, again, those are not apply for all scenarios. You have to figure out those source and loss terms individually. And most importantly, by definition or by design, Fock-Planck framework cannot resolve dynamics on a timescale shorter than the drift phase mixing. So any signature happened within a drift period, essentially Fock-Planck framework cannot reproduce that, cannot evaluate what is its effect on radiation belt dynamics. Here is a brief example on things can happen within a drift phase. So the top panel shows the spin average flux also measured by the REP instrument for different energies from 1.8 to 7.7 MeV. And across this whole orbit, we see there are very clear flux oscillations measured by different bound of passes for the valence probe. And if we zoom in and do the trending of the flux and extract those flux oscillation signature, we can get the bottom figure. And now we can see clearly their flux oscillations are energy dependent. Through detailed calculation, we actually confirm that these are so-called drift echoes of multi-MeV electrons, suggest there are very rich signatures within drift period. And during this specific event, these drift echoes actually lasted more than 10 hours. So there's no way for a Fock-Planck framework to reproduce those drift echoes since it acts on a time scale much longer than drift period, and thus it can it's very hard to argue if it can incorporate the effect of these drift echoes on radiation belt particles. And certainly, well, even if we claim, well, we just ignore the non-diffusive effect and focus on diffusion itself, still the Fock-Planck framework is not ideal in terms of the quantification of the diffusion coefficients have its intrinsic uncertainties. Well, in order to calculate those diffusion coefficients, we often need magnetic and electric field fluctuation on an almost global scale, which intrinsically we cannot get that from any observations. We don't have that spatial temporal coverage. And what's more, the variability of plasma and field conditions of specific event we are studying is a lot, and it's very hard to get a whole picture of that for a single event. For example, we know that cold plasma density and plasma pulse location matters a lot to plasma wave generation and its effect with radiation belt electrons. This figure from Edison et al. In 2021 shows, top panel shows the flux of 7.7 MeV electrons still measured by the valence probes, and bottom panel shows the electron density. And by those magenta dashed line, you can see, relatively speaking, anytime you have a significant enhancement in flux of 7.7 MeV electrons, we almost always can see a very steep drop in electron density outside of the plasma sphere, which suggests that cold plasma density actually has a significant influence on radiation belt electron acceleration. However, this is something can rarely be captured by any empirical models, essentially because they are corresponding to very extreme scenario, while empirical models are kind of averaging over a long time period. On the other hand, the outer boundary condition also matters a lot when it comes to the Fock-Planck frameworks, kind of like simulation. Sometimes we can even, well, a change in outer boundary condition can even change the whole results of the simulation. So that's super important to determine what is our outer boundary condition and what is the last close drift shell location, which, however, is not often available from observation itself. And certainly there are different solar wind conditions and different solar wind drivers, for example, CMEs and CIRs, that could have different effect on radiation belt populations, which we don't really have a good handle on how to incorporate them into our current framework, how to better understand their differential effect, etc. So now talking about all these limitations, well, again, well, we have a lot of limitations and challenges in ahead of us, but how could we better understand the radiation belt particle dynamics and eventually be able to solve this debate over the leading acceleration mechanism of radiation belt electrons? Well, certainly there are a lot of ways to remedy the limitations and challenges we just talked before. However, in order to get a more complete, well, I would not say complete, but a better solution, we would really need comprehensive multi-point measurements at various orbits throughout the outer radiation belt and even beyond, just because, well, we really need better spatial temporal coverage of radiation belt particles in order to better understand its behavior. For example, we want to know, we want to have geotransfer orbit satellite measurements, just like those bivalent probes, which can provide observations of trapped populations and waves. At the same time, we also want some low Earth orbit satellite measurements, which can provide measurements of those precipitating electrons, so to give us some idea of the radiation belt loss, since, well, loss and source are essentially a balance. And without knowing the radiation belt loss, we cannot accurately know how much radiation belt electrons are accelerated. And we might need geosynchronous orbit and even beyond satellites to provide us the outer boundary conditions we need in our simulation, since we know that outer boundary condition is critical for the Fock-Planck simulation to work. And certainly, while we always talk about enough spatial temporal coverage, we really want to have large constellations to improve that in order to have a better view of the systematic changes in radiation belt. And luckily, while that's not that out of reach, since we now have a low-cost solution to really probe one probe belt with spatial and temporal coverage, which is, well, small sets and CubeSats, They are relatively cheaper, and we can afford to build many of them to provide great spatial and temporal coverage to really give us a system understanding of radiation belt dynamics. So here are a few CubeSat missions and ongoing and current CubeSat missions of radiation belt dynamics and also instrument development plan. So at geotransfer orbit, we have GTOSat developed at Goddard by PI is Lauren Blum, and also our group is working on a high energy resolution telescope that is capable to measure ultra-relativistic electrons, hope to put into GTOSat to take high energy resolution measurements. And we also have quite a few LEO satellite CubeSats currently either is under development or is already launched. And some of them actually returned quite promising results that I know of. So all those demonstrate that, well, indeed, small sats and CubeSats would provide a low-cost solution to finally be able to provide radiation belt observations with sufficient spatial and temporal coverage. And sorry, I'm running a little bit long, but I still want to briefly discuss about our focus group activity for this year. So what you are expecting this year. We have 4 standalone sessions with 2 joint sessions with depolarization group and also comparative plasma magnetosphere group. So we still plan to run a panel discussion session, but we would have something new called a focus topic sections, which means we have focus topics in those sections, and then we solicitate presentations from different presenters to chime in, and we have open discussions at the end of the session to better to advance our understanding on those focus topics. And we'll specifically have an early career session devoted to students and early career scientists to do their presentation. And here is a list of our current potential focus topics. I won't read through in detail since I ran over time, but we welcome any suggestions and feedback. Please feel free to contact me at this email address if you have more idea on what you think would make a perfect focus topic. And if we have time, we can implement in this year. Even if we not, we can consider them for next year group activity. That would be perfect. So thank you all very much for your support and contribution. And I will stop here for my presentation.
Thank you, Hong, for a great talk. Sorry, my camera wasn't working and it just popped up. Thank you. I think you covered a lot. We are roughly at time, so we'll jump to Ben and then we'll come back to questions at the end. Eric and Elizaveta, we will come to you guys' questions at the end of Ben's seminar just to stay on time today. So our next seminar is by Ben Hogan. He will be following up Hong, giving update on some of his work with radiation belt dynamics. So Ben studied mechanical engineering for his bachelor's at Rutgers University before beginning graduate studies in space physics under Bill Locko at Dartmouth. During his master's, Ben worked as an advanced study program fellow at the High Altitude Observatory of NCAR and focused on magnetosphere ionosphere thermosphere modeling. Ben is now a PhD student under Professor Shinlin Lee at CU Boulder, and his current research interests include modeling of Earth's radiation belts and energetic particle instrument designed for measuring radiation belt populations. And I want to do one more apology. They're taking a tree down outside, so I apologize if the question period coming up might be a little bit loud. With that, Ben, if you want to take it away.
Sure. Thank you, Kyle, and thank you to the seminar for having me here, and thank you for all joining in here today. I'll be following up Hong's talk now with a little bit of our science results, showing you a little bit of what is going on within this focus group and what we're doing with some of the satellite data that exists there. And I'd like to thank my contributors. I'm a graduate student under Professor Shinlin Lee. And here I'll be using data from the REPT, EMPHASIS, and MAGFM teams from the Van Allen probes mission. So Hong talked a bit about phase space density. So phase space density is a great tool for mapping particles, whether those are protons, electrons, in coordinates relative to their adiabatic invariance. So we know that plasma particles in the radiation belts want to conserve their 3 adiabatic invariants. So if we hold the first and second adiabatic invariance constant, we can get nice little radial profiles of phase space density that normally look something like this. But we can have various physical processes that modulate phase space density. And those dynamics then become very apparent using this tool of phase space density rather than just using normal flux measurements from the satellites. So some effects that can happen include the DST effect. That's where, due to the reduction in the DST by the ring current, the amount of entrapped flux encircled by a particle can change. So the particles will change in radial distance from Earth in order to conserve their third adiabatic invariant. However, this is an adiabatic process, so this is reversible, but it is visible in phase space density over time. We can also see the effects of magnetopause shadowing. Hong talked a little bit about that, where we have particles that are trapped on last privileged drift shells, but during large disturbances, during geomagnetic storms, the magnetopause can move inward within certain drift shells, and particles on those drift shells will become rapidly lost. That's sort of illustrated here. We can also have the effects of radial diffusion, which Hong just talked about. Radial diffusion will exist to reduce gradients in phase space density and will transport particles outward when you have certain effects like these, or if any local minima or maxima develop in your phase space density profiles, radial diffusion will exist to reduce those gradients. And this is another figure from Lee and Hudson. Hong showed a good one showing the local acceleration, and sort of the opposite of that is precipitation loss. So we can have these local mechanisms where different wave particle interactions are occurring. So these waves happen, and they happen to be occurring at frequencies that match up with some of the invariant frequencies of the particles, and that can cause these particles to fail to conserve their adiabatic invariance, and oftentimes they can then travel lower down on their magnetic field line and interact with the dense atmosphere and precipitate down. And that looks like this in your phase space density profile. This can happen due to His waves, which occur commonly within the plasma pause, chorus waves, which can happen outside, and emic waves, which can happen all around. And I'll be talking about emic waves a bit more here. And Hong showed this figure as well. And I just want to show this here to illustrate where some of these processes can happen and how important these multi-point measurements can be. As we can see, there is spatial variation in a lot of these processes. So if we can make these multi-point measurements and make conjunction measurements, that helps our science greatly. So I want to talk about the emic wave a little bit. So emic waves are interesting because they can cause rapid loss of multi-MeV electrons, specifically without necessarily modulating the populations of lower energy particles. We observe these in the magnetic field and wave data from instruments, and they can also be observed at ground stations. They're generally confined to lower magnetic latitudes. And on the right here, I have an example of, this is a study from Maria Usanova et al. So this is plotting the early part of the Valon probes era. And this is showing electron flux measurements. So here we have flux measurements for some of the repped energy channels, and we can see there's a storm that occurs early in this time period here, late in October, and we can see how that reduces some of the multi-MeV electron flux. We also have plots like these. So from the repped data, which is measuring the multi-MeV electrons on the Van Allen probes, we have measurements that are pitch angle resolved. So if we normalize our pitch angle measurements to the 90-degree pitch angle measurements, we can see narrowing of the pitch angle spectrum happens during these storms. So this is saying that these emic waves are narrowing the pitch angle spectra and causing loss of our low pitch angle multi-MeV particles. Here is ground station measurements. So this is from the Charisma ground stations. These are search coil magnetometers scattered throughout Canada, and they measure for the presence of emic waves. So here we can see some example of how multi-point measurements are used to identify emic wave occurrences, and then what some of their signatures are in multi-MeV particles. When we look at them in phase space density, here's a study by Yuri Spritz from 2017, and we can see what this looks like. So this looks very similar to the cartoon that I just showed before from Lee and Hudson. And here we can see the local loss happening at multi-MeV electrons. This is happening for high energy electron species, but down here at only 1 MeV, we don't really see the same amount of fast local loss that's happening here on the order of satellite passes. So these are some of the characteristics of emic waves that we can see. And it's important science because this is what we think can help contribute to the third radiation belt. One of the early studies from the Van Allen probes era by Dan Baker showed the formation of a storage ring or a third radiation belt down at lower L values. And Yuri Spritz did some studies with some simulations showing that simulations with emic waves could produce these local losses and then create a storage ring of multi-MeV particles. But when he ran the simulations without the emic wave presence, he wasn't able to get that same reproduction of the third radiation belt. So a quick talk about where emic waves are preferentially observed. So here is the results of some studies by Sagan et al. This is earlier in the Van Allen probes era, studying only until about June 2014. And then here's a later study by Chen et al. Who looks all the way until June 2017. So this figure shows a nice spatial distribution of where we see different emic waves. So they predominantly occur in our major ion species bands, so our helium, hydrogen, helium, and oxygen bands. And we can see what the spatial distribution of these are, and particularly in what L values. As we looked at the prior plots, the results by Yuri Spritz et al. Showed that emic wave loss usually occurs around L equals 4 or greater. And we can see that's where a lot of these helium band waves are occurring, around 4 to 5 or so. Oxygen band waves can occur at lower L values, and the hydrogen band waves can occur at higher L values. So we did a study studying the middle of 2015. So 2015 was an interesting year for the Van Allen probes because they observed a very strong storm in terms of DST in March, and then a very strong storm in terms of DST in June. And we did a study looking at radial profiles of phase space density in between these two strong storms. And we could see during these strong storms, these are daily average phase space density radial profiles plotted every other day during this time period. And we can see that for these higher energy particles, so here at first adiabatic invariant values of 3000 MeV per Gauss, right here at L star equals 3.5, corresponding to 5 MeV electrons, we start to see a local minimum that develops in phase space density over the course of 3 months or so. And this is interesting, as I've plotted here at L star equals 3. This is what we traditionally consider to be the inner edge of the outer radiation belt. And what that does is by the end of this time period, it leads to the formation of a local maximum right along the inner edge of the outer radiation belt there. So this is the formation of this sort of storage ring or third radiation belt occurring near the inner edge of the outer radiation belt. And we're kind of seeing how it occurs or develops over this multi-month period. So this was an interesting observation, we thought, and we studied it by looking at specific events that happened during this time period. So right here, I want to draw our attention to this little dip in DST that happened in early June 2015. So there was a moderate storm on June 8th, 2015. DST only got down to -76 nanotesla. Here on the top panel is my DST plot for this time period. And I've color-coded 4 consecutive satellite passes here with their middle time plotted here. And in my lower plots here for different adiabatic invariants, first adiabatic invariants, I've plotted what is our phase space density radial profiles. And again, we start to see this energy-dependent behavior. So as we look at the highest energies, we start to see the greatest amount of decrease in phase space density. And here we're seeing order of magnitude decreases in 5 MeV electrons in orders of 1 satellite orbit due to only a relatively moderate storm. And these processes or these moderate storms seem to lead to the development of this local maximum at L star equals 3.5, which is an interesting feature normally not observed at this low L star in phase space density. We also looked at the normalized pitch angle spectra. So I just showed before how that can be a signature of emic waves. This is for the first 3 weeks of June 2015. And here's where this storm occurred that I just showed. And here I have daily average normalized plots of our pitch angle spectra for some of the multi-MeV energy channels here as viewed by REPT. And we can see that for all of these, we see pretty good narrowing of the pitch angle spectra all the way up to almost 6 MeV electrons. So this is indicative that emic waves could also be causing this, as well as the features we see here. We also looked at the plasma density. So this is derived from the wave data on RBSP. So this is the emphasis instrument. And from the upper hybrid frequency, we can back out the electron number density. So that's shown on the right y-axis here in green. And on my left y-axis in blue, I've shown the L star of the satellite. And I've shown where the satellite is passing through L equals 3.5. And we can see that during this event, L equals 3.5 is within the plasma sphere. The gray areas here are the plasma sphere location, denoted by Craig Kleitzing. So we can see that whatever process we're trying to observe at L star equals 3.5 that's causing our local minimum is happening within the plasma pause. And then we can also do a pretty detailed analysis of that magnetic field data from the emphasis measurement as well. So here we have done studies of the wave power, wave normal angle, and ellipticity of the wave and scanned for signatures of emic waves because we see these characteristics in our observations that are consistent with the emic wave. So here I've plotted the ion gyro frequencies, and an emic wave will become apparent below the gyro frequency of interest. So here we can see some emic waves that are occurring in the helium band during the first 6 hours of June 8th. Here we have some background contamination. We looked at RBSPB, and that's not present. And we also see some regions of extended power with no cutoffs at the gyro frequencies. So this is also considered instrument contamination, but we see some nice signatures here of emic waves in the helium bands. And if we look closer at some of these signatures, and we do take basically a vertical slice here and average the power, we get a nice Gaussian peak. And a Gaussian peak is also a signature of emic wave power, or characteristic of emic wave power. So, all of our observations here are consistent with loss due to emic waves, and we think that they're a valid investigator here of what's happening. So we don't think that it could be the DST effect. This continuous decrease we're seeing happens over a multi-month period, as I showed earlier on. Radial diffusion probably isn't at play because that would actually be opposing local gradients like these. Magnetopause shadowing probably isn't present because we see constant phase space density at higher L star values. So wave particle interactions seem to make sense, not just because of the cartoon that we showed from Lee and Hudson, but also because of the physics and the observations that we're seeing here. So this is happening within the plasma pause, so it's probably not chorus waves. We saw those happen outside the plasma pause generally. His waves do happen in the plasma pause, but on much lower timescales, slower timescales, and they generally affect lower energy electrons. Emic waves, we see those during this time period, and they're shown to cause many similar local minima and phase space density, however, at higher L star values. So it's interesting that these local minima are forming all the way down to these low L star values. So we did some studies to try to play around with diffusion coefficients and see, can some of this physics that Hong talked about using the Fokker-Planck model, looking at diffusion coefficients, can we start to explain some of that? So here I've plotted the diffusion coefficients, are plotted in color on my right y-axis here, and color denotes the strength of the diffusion coefficient. And the diffusion coefficient is roughly 1 over the timescale of loss that's observed. And on this first panel here, I want to focus, this is our pitch angle diffusion coefficient. So that relates to how fast the particles are being scattered away in pitch angle due to the process present. And we looked at what are the effects of helium band emic waves and oxygen band emic waves. Helium band emic waves, as we've shown, were fairly prevalent and also observed during our time period. However, energy is on my y-axis here, and we see that the minimum resonant energy, or the minimum value for which we have valid diffusion coefficients, is much too high. This is in the 20s of MeV. However, if we look at oxygen band waves, our theory shows that we can actually get diffusion coefficients that are fairly strong for these multi-MeV electrons, and this is consistent with our observations. And we also showed earlier by some of our statistical studies that the oxygen band waves do happen at lower L values. So this leads to some questions as to could these oxygen band emic waves during certain conditions be causing these interesting features in phase space density. So in the future, we want to solve a pitch angle diffusion equation. So Hong talked about how we have these Fokker-Planck models, and we've made a lot of assumptions in assuming these or calculating these diffusion coefficients. But if we use that to then solve our diffusion equations, can we recreate these observations that we showed? So these are just satellite pass averaged radial profiles of phase space density. And if we look at just the phase space density at L star equals 3.5, we see these sort of features. So Hong was talking a little bit about how we can have some discrepancy in our magnetic field variations and our other assumptions that go into these PSD calculations. So over here, we can see that there's a very obvious decrease in our phase space density extending for many satellite passes after this event here. So if we can use theory to explain this, why is it happening at these low L star values? Normally, I showed the results of Spritz where these happen at higher L star values. 4 other studies show these minimums can happen up to 4.5. And we show that they don't really happen that often at low L star value, but these are very important in the formation of things like our third radiation belt or our storage ring of multi-MeV electrons. And as we're looking at this data as well, we're also asking, are there other spacecraft that could have been observing loss features during this time period? So Hong talked about all these other satellites that are up there. There's POSE, which is measuring precipitating electron flux and proton flux. And we want to look at those data as well to see if we can find some sort of conjunction measurements to add to the credence of our idea that emic waves are contributing to this effect here. And that's the work I have here. Thank you for listening, and thank you again for having me. And I think we'll have some time for questions. Thank you.
Thank you, Ben, for a great talk. So we do have a couple questions coming from Hong's initial talk, but I think that also apply to your talk. So if you guys are interested, we can get an opinion from both of you. So Eric is asking, since several of the processes involved operate on timescales shorter than the Van Allen probe orbit, how much can we distinguish the acceleration mechanisms, or in the case of yours, Ben, the loss mechanisms, from one of these radial profiles?
Yeah, that's a great question. Maybe I will let Ben to answer first. And
yeah, I mean, that's a very relevant question to what I just showed, right? Where we're showing some sort of interesting observation that happens within a satellite orbit, and we're trying to tease out what physical mechanism is happening. We think that the particles tell the data. Our drift periods are faster than the satellite orbits, so the information of whatever loss process happened is then getting around to the satellites within that orbit. So that's why we kind of are looking at the flux observations almost more than signatures of the mechanism itself. And also we're trying to tease it out by looking at theory. So if we can show this with our current understanding of Fokker-Planck diffusion equations, and that contribute to a certain amount of the loss feature. So say we can account for 70% of the observed phase space density loss due to this mechanism, then we could say, okay, there's something happening, but obviously there's other processes that are not always going to be observed. So it's kind of a balance of trying to use some theory to explain it, while also acknowledging that, yeah, we can't truly capture all of the variations happening with just 2 satellites in the case of RBSP, or even the large amount we have up now.
yeah, I totally agree with Ben's comment. Indeed, for Van Allen probes, we only have 2, which is not giving us fast enough spatial temporal resolution we want. So in this case, it's very hard to purely rely on the radial profile of phase space density itself to distinguish between different acceleration mechanisms or loss mechanisms. The best we could do, one thing is, based on current data, maybe we can do some statistical analysis, just like Alex Boyd did in 2018, I believe. He used both Van Allen probes and SEMIs to try to find this locally growing peak in phase space density. And by applying this to a large enough database, we can have some sort of statistical understanding on, well, how much one of the acceleration mechanism works in like how many percentage of events. then certainly we know for some events, this categorization would be wrong. However, since we apply that to enough number of events, we can still get a ballpark out of it, so have some sense. But indeed, in order to fully solve this question, I'd say we still need better spatial coverage of measurements, which could mean that multiple violent probe-like satellites in geotransport orbit to take data at a much better spatial and temporal coverage. We have better coverage on LEO, which, well, like poles, we have multiple poles, and we have all these LEO orbit CubeSats. If they're operating at the same time, we could get very really multi-point measurements, not just two. However, LEO has its own limitation, like it's only measuring those very low equatorial pitch angle particles. So we would never get those near equatorially trapped populations, how they get accelerated from LEO measurements. So I'd say the ultimate solution, hopefully, still lie with we need to provide that multi-point observations, maybe through a low-cost way of CubeSats and small sets, just constellations of them to measure better spatial temporal coverage, flux data, and eventually phase-space density.
Excellent, thank you. So Elizaveta has a question regarding a DST regression with the radiation belt location. I don't know if you've had a chance or if you know about it, Hong. It's the I'm not going to be able to say it right.
Skya relation, yeah.
Yeah, connected
yeah,
to minimum DST.
Right, I read that. And actually, yeah, one of my early papers, I believe that's 2013, we actually investigate a bit on the Tversky relation, which is essentially correlating the minimum DST versus the location of the maximum flux of alteration belt. And they actually show quite good correlation if you consider like many events we are focusing on, many storms we are focusing on. We figure out that's not just the maximum flux in the alteration belt. There's also many other quantities like the enhanced flux and the peak locations, the innermost locations, etc. They all have relatively good correlation with the minimum DST during any storms. However, I do want to point out that that's statistical relation. So if you investigate a wide range of storms, and yes, in general, we can get a quite high correlation coefficient. I don't remember exactly the number, but I think we can get at least 2.7.8. But if we do R-square, that still only tells us about like 50% each of variations. And also when we look at individual storm, it may not be the case. So we could have a small storm that's causing a very significant enhancement, as there's one paper we published in, I think it's in 2018, and we studied a small to moderate storm. The minimum DST is only -50 nanotesla, but we see the radiation belt electron enhancement all the way up to 7.7 MeV. And I think recently I saw a recent publication to conduct a 3D Fokker-Planck simulation of this specific event, and indeed they got very rich results to show that even during a small to moderate storm, we still have those very significant enhancement event in the outer radiation belt, and it's not like directly related to the storm intensity, but rather tied to a lot of different variables like cold plasma density, wave activity, etc. So I think, yeah, in general, Tversky relation is quite useful in telling us that on average, if you have a stronger storm, indeed you expect to have stronger enhancement or at least a lower penetration of outer belt electrons. However, that's not always the case when it comes to specific storms. So that's always good to keep in mind. And our understanding of the radiation belt so far is not enough to really predict the final outcome of the radiation belt after a storm. So I'd say there's still a lot of work to be done on that.
Excellent, cool, thank you. That was a great answer. I think you covered a lot of important topics and ideas that have come from the Van Allen probes there. So that's all that we have today. Thank you, Ben and Hong, for 2 wonderful talks. We will be on a short break for the next few weeks with the seminars, and we will come back on June 12th for our next set of seminars. So thank you again, guys. I hope you all have a wonderful week, and I look forward to seeing everyone after our break.
Thank you. Bye.
Thank you.
Bye.